Hello, 大家好. I'm Leo Dirac, and I'm going to talk to you today about industrial scale deep learning with Apache MXNet. I am a principal engineer in the Amazon AI group in Amazon Web Services. And I'm going to tell you about industrial scale deep learning, and I'm going to start out by telling you exactly what I mean by that, because we've been hearing a lot about industrial applications today. And then I'm going to dive into Apache MXNet and see how it performs really well on these problems. Then we'll take a technical deep dive into some of the math and theory on distributed deep learning. And then we'll pop that out and see how you can apply these ideas in practice. So what do I mean when I say industrial scale deep learning? So it's not trains and mines and some of the other things that we've been hearing about. What I mean here, although it could be, what I mean here is advanced artificial intelligence applications that are deployed to millions of customers through industrial products, like the speech recognition and natural language understanding in the Amazon Echo and Alexa family of products. Or the new Amazon Go retail store, which is a new kind of shopping experience where you can browse the shelves and put things into your bag, and at the same time, advanced computer vision and deep learning systems put those same items into a virtual shopping cart for you, so that when you're done, you can just walk out. And all those items are charged to your Amazon account automatically with no lines, no checkout. It's really pretty cool. At Amazon, we have thousands of engineers building AI applications across fulfillment and logistics, our delivery systems, search and discovery of our product catalog, other existing products, and new products that haven't been released yet. And a thing that draws all these things together is that they're built by large teams of data scientists working in conjunction with teams of software engineers on truly massive data sets. The sizes of data that we have available in industrial settings is much larger than what's typically used for academic research. And so that really changes the scale of things. And that's what I mean when I talk about industrial applications of deep learning. And I think we all understand that speed matters. If you can't innovate quickly in this environment, you're going to get left behind. But training deep neural networks can take a really long time. Consider the AlexNet that Alex Kruszewski built and used in 2012 to win the ImageNet competition. And this really did a lot to spark the deep learning revolution. That took him about 3 weeks to train and about 1,000 GPU hours. And then a few years later, the ResNet 152 architecture was 4 times more compute hungry than that. And today, a state-of-the-art neural machine translation system takes about 14,000 GPU hours to train. Whereas there was recently published a comprehensive sweep of hyperparameters and model architectures to tune neural machine translations, and that clocked in at 250,000 GPU hours. Now, clearly, you can't have your researchers waiting for 250,000 hours to get the results. It's just impractical. These workloads need to be spread out across a fleet of machines to get results done at any speed. So scientific productivity is, in a very real sense, determined by how quickly you can iterate on your ideas. So if a researcher has a new idea about a neural network and she wants to try it out, she has to train a neural network and set that job running. And it's not until the job is done that she'll find out if those results are good enough to build upon them or if she needs to try something else. And so the speed of her iteration is really determined by how quickly that training job can finish. So if that's running on just a single GPU, then it can take orders of magnitude longer than if it's running on a fleet of GPUs, either within a single machine or distributed across a fleet of machines themselves. This brings me to Apache MXNet, because this is one of the things that Apache MXNet is really great at. So MXNet is a software package that we love at Amazon and we support heavily. But if you look at the numbers, only about 1/3 of the contributions to MXNet come from within Amazon. Others are coming from Apple and Tesla and Microsoft and lots of top academic institutions. And its growth rate is outpacing a lot of popular deep learning frameworks. You can program MXNet in a variety of programming languages. Of course, there's Python. But there's also a high-performance C++ interface for Internet of Things and embedded applications. There's a Scala interface for Spark programmers and other people working in JVM. And data scientists who are familiar with R or Julia or MATLAB can start to deploy deep learning techniques using MXNet without having to change their programming language. When you throw in JavaScript and Go, you see that that MXNet is an extremely flexible way to implement deep learning solutions across a variety of front ends, and those all work together on the same backend, which is written in C++ and CUDA to get maximum efficiency out of the hardware that you have available, regardless of which kind of front end you're working on it from. Here's a set of benchmarks that back up that idea. What we're doing here is we're training a classic ImageNet 1K problem, the ImageNet image classifier, across a number of GPUs, starting with just one and then going up to 16 GPUs, all within the same machine. And that red line represents the ideal scaling if all of those GPUs are being used perfectly to their fullest extent. And what we see just below that is that the Inception architecture and the ResNet architecture, when running on MXNet, scale at over 90% efficiency. And that's within one machine. Now, when we need to go bigger and scale out to lots of machines, here's that same benchmark out to 16 machines, where each of those machines has 16 GPUs, for a total of 256 GPUs. And we see that even at this scale, MXNet can maintain almost 90% scaling efficiency. And the result is that a training job that would have taken weeks to finish is now reduced to just a matter of hours. And that's without any loss in validation accuracy. It's just faster, and it just improves your productivity. OK, so that's cool, right? But how does it work? How do we do that? So let's take a bit of a technical deep dive into the theory of how distributed deep learning works. And we'll go through some of the mathematical concepts. So to start out with, let's think about some ideas about how we might speed up a distributed training job. Like the simplest one to start with is just use bigger machines, classic vertical scaling. And this works to a certain extent. Today, in AWS, you can turn on P2 16x large instances that are capable of 70 trillion floating point operations per second. That's pretty fast. And I know we're all super excited about the next generation of deep learning hardware accelerators that are going to be coming online at the end of this year, which are going to be way, way faster than this. But these P2 instances are available today at scale to solve your industrial problems. So if we look inside one of these things, it has 16 GPUs working together, communicating over a high-speed PCI Express bus that is capable of moving 15 gigabytes per second about between the GPUs. So that's how we get really good scaling within a single machine. But at some point, you have to go beyond one machine, because there's a practical limit to how many GPU devices you can put inside of a box. So when we start looking at more machines, the architecture is pretty straightforward. You turn on a lot of these EC2 instances that each have 16 GPUs, and they're connected by this high-speed Ethernet, which is capable of moving about 20 gigabits per second. And this multi-host distribution strategy is usually trained with an algorithm called data parallel training. And here, the data is divided evenly amongst each of the workers. Each worker gets a subset of the data, and it just works on that. But each worker also has a full copy of the entire neural network model. And importantly, they collaborate to produce one shared model at the end, because we just want to get a single neural network out. And exactly how they do that collaboration is really the crux of the issue. And that's what we're going to dive into. So to understand that, let's talk about SGD, stochastic gradient descent, which is the algorithm that's almost always used to train neural networks. So to visualize SGD, we're going to look at this loss surface. And here, higher on this loss surface means larger errors and a less accurate network. And so we're trying to find our way down to the bottom of these valleys, where the neural network is giving its best accuracy. And in this visualization, I'm pretending the neural network only has 2 parameters, and so it's a 2-dimensional manifold, whereas real industrial neural networks have millions, tens of millions of parameters. But it's pretty hard to draw and visualize a 10 million dimensional manifold, so we'll just stick with 2 to keep it simple. Now, any individual neural network is a point on this manifold, a point on this space. And the SGD algorithm runs backprop to estimate which way it thinks is down from where it is, given the subset of data it has, and then takes a small step in that direction. And you repeat that until you get down to a nice minimum. Now, when you need to distribute this across a fleet of machines, each of those machines is working with a different subset of data, and so each of those machines is going to get a different estimate of which way is down from wherever they are. So to keep these workers from diverging as they work their way down this loss surface, they need to communicate with each other what the estimate of the gradient is that they found. And so a simple way to do that would be to just have every worker tell every other worker the gradient update that they found. And this works, but it scales really badly, right? You need n-squared communication for n workers. And so you quickly run out of network bandwidth. Now, how do you deal with this? Well, one approach is just to use faster networking. And you see in the literature, sometimes people talk about building these research clusters with really fast InfiniBand network. And that helps to a certain extent, but you're not addressing the fundamental challenge, which is that the scalability is limited by this n-squared term in the amount of bandwidth you need. So faster networking doesn't really get you where you want. What you need is a way to make your communication itself more efficient. So instead of having every worker talk to every other worker, best practice is to use a parameter server, where each worker just sends its gradient message up to the parameter server, and then the parameter server aggregates all of those messages together and sends them back down. Once we've done this, we only need order n bandwidth for n machines. So this scales much, much better than the naive strategy. However, there's still a scaling bottleneck, which is that parameter server and the amount of network bandwidth it needs, because all of those gradient messages are being concentrated on that one machine. And so the physical network interface on that parameter server becomes the bottleneck, even though its computational job is very simple. It just needs to add together these gradient messages and send them back out. The solution to this problem is actually fairly straightforward if you understand what the parameter server is doing, which is just adding these vectors together, because that job is trivially shardable across a fleet of machines. So if you shard the parameter server across a fleet, then you've reduced the problem so that each machine only needs a constant amount of bandwidth, no matter how wide you scale out. And this should be clear for the workers, because at each step, the workers are just sending out a gradient message and receiving a gradient message. So that amount of bandwidth is constant no matter how you scale out. It's a little less obvious, but the same is true in the parameter server, because each step, it's receiving n messages, but the size of those messages is going down the wider the fleet is. So the size of the messages is 1 over n. So again, the amount of bandwidth needed by the parameter servers is constant as you scale out. And this strategy, it looks complicated, and it is to execute it efficiently, but MXNet does this automatically, and this is the strategy that MXNet uses to achieve that really excellent near linear scaling up to a very large number of GPUs on the benchmarks that I was showing you earlier. So it's a great strategy. Now, in some cases, it's possible to do even better than this. So what I was just referring to is called synchronous distributed SGD. And there's a bit of a limitation in it if you think about the timing of what's going on. Now, each of those workers is simultaneously going to be calculating its estimate of which way is down, and that uses the compute resources. And then it sends those messages out to the parameter server and waits for the parameter server to get all the messages to send them back. And in that waiting time, the compute resources are sitting idle. And not until the parameter server comes back do those compute resources start up again, and the network takes a step and repeats itself. So there's an opportunity to improve by removing that idle time during the network. So we use a trick from distributed systems research, which is to overlay the computation and the networking. And here, what you get is called asynchronous distributed training. And how this works is, again, each of the workers calculates its estimate of which way is down, and they send off that message to the parameter server, but they don't wait for the parameter server to send the response before they take a step, and then they start calculating their next gradient, and they keep going. And in this way, you can keep the compute resources on the fleet running almost continuously and increase efficiency. Now, this comes with a cost, because as you can clearly see, the workers are starting to diverge on the loss surface, and there's no guarantee that they're going to end up in the same place at all. So there's a variety of tricks and different techniques in the literature for how to keep them together, or more or less together, or somewhat together. And this is a really interesting area of research, and it seems like it might be problematic. And it can blow up in your face. It's kind of unreliable. But if you do it correctly, you can actually get better results using asynchronous training than you can with synchronous. My colleague Nico Strum, who works on the speech recognition system in Alexa, published this paper a couple years ago, where he shows nearly a 2% error reduction in word error rate on a speech recognition task by using asynchronous training compared to the same amount of work if it was done synchronously. Now, this is odd and maybe a little bit counterintuitive. So I'll try and explain what's going on and tell you why it makes sense to me, at least, that you can get better results with asynchronous training. So here, this work was originally done by Jürgen Schmidhuber, who gave the keynote this morning, and Sepp Hochreiter 20 years ago, and it was kind of rediscovered last year. And we're looking at the loss surface again, but now projected down to just one dimension for simplification. And the idea is that there are different kinds of minima. It's non-convex, so you can have different bottoms that you might land in. And some of those bottoms are called sharp minima, where the sides of the loss surface go up very quickly, and some of them are flat. And there's research showing that if you end up at the bottom of one of these sharp minima, your network is going to generalize less well than at the bottom of the flat one. So even though it's the same value on the loss surface, you get better accuracy out of a flat minimum than a sharp one. Now, it's intuitive to think that if you have just a single worker finding its way down the loss surface, it's likely to end up at the bottom of a sharp minimum, because it finds its way down there and it just willows its way down. But if you have a swarm of workers that are exploring the loss surface kind of collaboratively, it's less likely for that whole swarm to get stuck down in that little valley, and it's more likely for it to settle down in one of these broad minima. And so I think that's a good intuitive explanation for why asynchronous distributed training is likely to give better results than synchronous training. Now, I must say, this interpretation of the loss surface is somewhat controversial. And Bengio's lab put out a paper earlier this year, which is a direct rebuttal to this idea. And it's a good read if you're interested in this kind of thing like I am. But there's a lot of math, right? There's a lot of details going on here. So let's pop back out and talk about how you actually put these ideas into practice. Because it's great to talk about how you get, orders of magnitude improvements in your training time, but you actually have to code it. And in a lot of deep learning frameworks, well, in some of the older ones, it's just not possible at all. But in other deep learning frameworks, if you want to put these ideas into practice, you need to understand all that theory I was just talking about and be a good distributed systems programmer to be able to achieve good efficiency across your fleet. But with Apache MXNet, it's actually very easy to do all of this. And I'll show you by diving into the code to actually do training of an ImageNet model using ResNet. Now, here's the code for single GPU training. It starts out with creating the ResNet object with all 152 layers, and that gives you the symbol object, which is a pointer to the end of the computational graph. Then we create the context object, and we bind those two into a module, and then the module is the thing that we train by passing in the training and data evaluation data. And then we also pass in the optimization arguments like the number of epochs. Now let's focus on that one line, which is defining the context object, which GPU to use. If you want to change this code to be able to use multiple GPUs within a machine, that is the only line of code that you need to change. Instead of passing in a single context object with a single GPU, you just pass in an array of GPU objects for all of the GPUs in your machine. And voila, you're now running 15, 16 times faster with one line of code change. Now, if you want to go even bigger than that and go out to multi-host training, in a lot of cases, you don't need to change any of that code at all. You just need to execute the process differently. So MXNet has this launcher script where you configure it with the number of machines you want, 16, how to connect to those machines, SSH in this case, and the addresses of them, and then what command to run. And as long as that code is on all of the machines and they all have access to the same data set, then it sets up that distributed parameter server that I talked about and does the distributed computation for you. And it actually reuses the same machines for computation and for the parameter server, because the parameter server's job isn't very compute heavy in the big picture. And this will run either synchronous distributed training or asynchronous, depending on how you configure the KV store, which is another term for the parameter server. And so in this way, MXNet achieves great separation of concerns between different tasks in a data science workflow. There, you can have people working on the data side of things, people focusing on the science, on the neural network and the loss and the objective, and then a completely different group thinking about the hardware and how to get this to run efficiently across all of the hardware that you have. And this separation is really great because it means that it's easy to get high performance out of a fleet of machines with MXNet, and you don't need to understand all of these technical details about distributed deep learning. So what I've showed you is that Apache MXNet gives you easy access to advanced optimization science for distributed deep learning. With just a very small amount of code, you can go from a simple research idea out to something that can run orders of magnitude faster and greatly improve your scientific productivity when working on these industrial scale problems with truly massive data sets. And with that, I'll thank you for your time.